All right, so now we're going to talk about surface friction. So again, talking about the concept of what it is and drawing the free body diagrams associated with it. So we're going to start again with our examples, just like we did with air resistance, where we're just going to draw them out. So a 13-kilogram object is pushed with a force of 10 newtons on a frictionless horizontal surface. So when we do these surface free body diagrams, we are strictly going to be worried about horizontal surfaces. So all the assumptions we are about to make are specific for horizontal surfaces, not for angled surfaces. We're not going to worry about angled surfaces in this class, but I just wanted to make sure that everyone knew that there is a difference. So we are making assumptions based on horizontal. So the first thing is if you know that a surface is involved, when you start your free body diagram, you draw the surface underneath it. So now we know, just looking at the picture, that our object is on a surface. The first thing we're given is 13 kilograms. Kilograms measures mass. This goes inside the box. The next thing we're given is the pushing force. And so if you remember back to the video that dealt with drawing free body diagrams, then you know exactly where this one goes. So this is your applied force. So we'll do forces in purple again. So this is your applied. Your applied force goes in this direction, except straight up and down, or straight across. With this horizontal. There we go. So our applied is 10 newtons. Now, since it's frictionless, then that means our frictional force is equal to 0. So there is no arrow going this way. So frictionless means no friction. But we're still missing two very important arrows. One is that the object has a weight pulling it down. And the other is that the surface is pushing up. So again, just like I tried to emphasize in the video where we drew free body diagrams, this is not the air resistance, because this is a surface. This is the surface pushing back up on the object. So this arrow is what we called the normal force. So normal force. This is the force due to gravity. That's our weight. So we can always find weight if we have the mass. 13 times 9.8. So weight is mass times acceleration due to gravity. And so our weight is equal to 127.4 newtons. Also in the free body diagram video, we talked about how on a horizontal surface, so specifically to horizontal, the normal force is equal to the weight. So the normal is 127.4 newtons. So here's your free body diagram. And now we need to find net force. Since we have two directions going on, we need to look at the net force in both. For a horizontal surface, the net force going up and down should always be 0 because the weight is equal to the normal. So the 127.4 minus 127.4 is 0. So now we're just looking left and right. And so if we look left and right, the only force we have is the supplied force. So our net force here is equal to the applied force, which is 10 newtons. From there, we find our acceleration using our F net equation. So F net equals ma. We have a net force of 10 newtons. We have a mass of 13 kilograms. And we're looking for A. So then all we have to do is solve for the acceleration by dividing by 13, and we get an acceleration of 0.769 meters per second squared. So just like with the air resistance ones, you take the free body diagram to find your net force, then you use your net force to find acceleration. Exactly the same way. All right, so let's do another example. So it says a 70 Newton object is pushed with a force of 20 newtons on a horizontal surface. If the friction force is 5 newtons, draw a free body diagram and calculate the net force and acceleration. All right, so let's start with our box. Our box is on a surface, and then we have our arrows. We always have weight, we always have normal, and now we're pushing with a certain force, and we have a frictional force. So now we need all 4 arrows. Now we got to figure out what they all are. So newtons are always a force, and so since it's a 70 Newton object, then the newtons go with the object, so that's your weight. So FW equals 70 newtons. It's pushed with a force of 20 newtons, so you are pushing at this force, so this is your applied. The frictional force is 5 newtons, so that's FF. Friction force always opposes the applied force. And then our last arrow up here is that normal force again, which we said is always equal to the weight. So there's all of our forces. So all we need now is to fill in the center. So we use our weight equation for that one. So our weight is 70. We're looking for mass, and gravity is 9.8. So dividing by 9.8 gives us a mass of 7.14 kilograms. So that goes inside the box. So now we need to find net force. So again, if you're looking in the up and down, these cancel out. So we're looking strictly left and right. So F net is equal to applied minus friction. And so we have a net force of 15 newtons. And then we use our F net equation to find the acceleration. So our F net is 15. We found our mass as 7.14, and we're solving for A. So we're going to divide by 7.14 and get our acceleration of 2.101 meters per second squared. So use the picture to find net force, use net force to find acceleration. All right, so let's try one more. We have a 10 kilogram object is pushed at constant velocity. So let's start with our box. And it's on a surface. And now we're given 10 kilograms. 10 kilograms is our mass. Mass goes inside the box. So 10 kilograms. We have weight pulling down. We have the normal pulling up. We have a frictional force. And we want to know what is the force that the object is pushed at. So we need to find the applied force. Let's make sure that is nice and horizontal. There we go. Okay, so let's go ahead and label here. The surface exerts frictional force of 9 newtons. So that's frictional force. Then we can also find these two, like we've done before. Weight is mg, 10 times 9.8, so 98 newtons, which means our normal is also 98 newtons. And then finally, we need to figure out how this constant velocity comes into play. So actually, let's underline that in blue. So constant velocity means there is no acceleration. So if we look at F net equals ma, if the acceleration is 0, the net force has to be 0. So constant velocity means net force is 0. Remember, there were 2 instances where net force is 0. One is it's pushed at constant velocity, the other is it's standing still. So this one is constant velocity. To have a net force of 0, we have to make sure that all of these cancel out. So 98, 98, 9, and 9. So I know it seems kind of silly to put these two in right now, the weight and the normal force, but trust me, you want to go ahead and get used to putting those in, because when we get to coefficient of friction, which is the next video, you will need this normal force in order to solve for the frictional force. Okay, so just make sure that you put these even though we're not really dealing with them right now.